हेलो फ्रेंड। तो स्टार्ट करते हैं 11th क्लास की केमिस्ट्री यूनिट 1 सम बेसिक कॉन्सेप्ट्स ऑफ केमिस्ट्री ऑब्जेक्टिव्स। आफ्टर स्टडिंग दिस unit you will be able to appreciate the contribution of India in the development of chemistry, understand the role of chemistry in different spheres of life, explain the characteristics of the three states of matter, classify different substances into elements, compounds and mixtures, use scientific notations and determine significant figures, differentiate between precision and accuracy, define S3, SI's base units and convert physical quantities from one system of units to another, explain various laws of chemical combination, appreciate significance of atomic mass, average atomic mass, molecular mass and formula mass, describe the terms of mole and molar mass, calculate the mass percent of component elements constituting a compound, determine empirical formula and molecular formula for a compound from the given experimental data, and perform the stoichiometric calculations. Chemistry is the science of molecules and their transformations. It is the science not so much of the hundred elements, but of the infinite variety of molecules that may be built from them. Roald Hoffman. Science can be viewed as a continuing human effort to systematic knowledge for describing and understanding nature. You have learned in our previous classes that we come across diverse substances present in nature and changes in them in daily life. Curd formation from milk, from formation of vinegar from sugarcane juice, on keeping for prolonged time, and rusting of iron are some of the examples of changes which we come across many times. For the sake of convenience, convenience, science is subdivided into various disciplines: chemistry, physics, biology, geology, etc. The branch of science that studies the preparation of properties, structure, and reactions of material substances is called chemistry. Development of chemistry. Chemistry, as we understand it today, is not a very old discipline. Chemistry was not studied for its own sake, rather, it came up as a result of search for two interesting things: philosopher's stone, Paris, which would convert all baser metals, etc., iron and copper, into gold; elixir of life, which would grant immortality. People in ancient India already had the knowledge of many scientific phenomena much before the advent of modern science. They applied that knowledge in various walks of life. Chemistry developed mainly in the form of alchemy and lateral chemistry during 1300 to 1600 CE. Modern chemistry took shape in the 18th century Europe after a few centuries of alchemical traditions which were introduced in Europe by the Arabs. Other cultures, especially the Chinese and the Indian, had their own alchemical traditions. These included much knowledge of chemical processes, of techniques. In ancient India, chemistry was called Russian Shastra, Rastanastra, Ras Kriya, or Ras Vidya. It included metallurgy, medicine, manufacture of cosmetics, glass, dyes, etc. Systemic excavations of at Mohenjo-daro in Sindh and Harappa in Punjab prove that the story of development of chemistry in India is very old. Archaeological findings show that baked bricks were used in construction work. It shows the mass production of chemical process in which materials were mixed, molded, and subjected to heat by using fire to achieve desirable qualities. Remains of glazed pottery have been found in Mohenjo-daro. Gypsum cement has been used in the construction work. It contains limestone sand and traces of carbon chloride, CaCO3. Harappans made fans short of glass which was used in of objects from metals such as lead, silver, gold, and copper. They improved the hardness of copper for making artifacts by using tin and arsenic. A number of glass objects were found in Musky in South India 1000 to 900 BCE, and Hastinapur and Takshashila in North India 1000 to 200 BCE. Glass and glaze were colored by addition of coloring agents like metal oxides. Copper metallurgy in India dates back to the beginning of Chalcolithic cultures in the subcontinent. There are much archaeological evidences to support the view that technological technologies for extraction of copper and iron were developed indigenously. According to Rig Veda, tanning of leather and dyeing of cotton were practiced during 1000 to 400 BCE. The golden gloss of the black polished ware of northern India could not be replicated, and it is still a chemical mystery. These wares indicate mastery with which kiln temperatures could be controlled. Kautilya's Arthashastra describes the production of salt from sea. A vast number of statements and material described in the ancient Vedic literature can be shown can show to agree with modern scientific findings. Copper utensils, iron, gold, silver ornaments, and terracotta discs and painted grey pottery have been found in many archaeological sites in North India. Susha- Sushruta Samhita explains the importance of alkalis. The Charak Samhita mentions ancient Indians who knew how to prepare sulfuric acid, nitric acid, and oxides of copper, tin, and zinc. The sulfates of copper, zinc, and iron, and the carbonates of lead and iron. Rasopanishada describes the preparation of gunpowder mixture. Tamil texts also describe the preparation of fireworks using sulfur, charcoal, saltpetre, that is potassium nitrate, mercury, camphor, etc. Nagarjuna was a great Indian scientist. He was reputed chemist and alchemist and metallurgist. His work Rasratan Rasratan Kar deals with the formation of mercury compounds. Here, he has also discussed the methods of the extraction of metals like gold, silver, tin, and copper. A book, Ras, mm, Ars Sarnavam appeared around 800 CE. It discusses the uses of the various furnaces, ovens, and crucibles for different purposes. It describes methods by which metals could be identified by flame color. Chakrapani discovered mercury sulfide, and the credit for inventing soap also goes to him. He used mustard oil and some alkalis as ingredients for making soap. Indians began making soaps in the 18th century. See oil of aranda and seeds of mahua plant and calcium carbonate were used for making soap. The paintings found on the walls of Ajanta and in Ellora, which would look fresh even after ages, testify to a high level of science achieved in ancient India. Var- Varahamihir's Brihat Samhita is effort of encyclopedia, which was composed in the 6th century CE. It informs about the preparation of glutinous material to be applied on walls and roofs of houses and temples. It was prepared entirely from extracts of various plants, fruits, seeds, and barks, which were concentrated by boiling and then treated with various resins. It will be interesting to taste such materials scientifically and assesses them for use. A number of classical texts like Atharva Veda 1000 BC mentions some dye stuff. The material used were turmeric, madder, sunflower, orpiment, cochineal, and lac. Some other substances having tinting property were campisica, Patanga, Jatuka, Varahamihir, Brihad Sanhita gives references to perfumes and cosmetics. Recipes for hair dyeing were made from plants like indigo and minerals like iron power, black iron, and steel, and acidic extracts of sour rice gruel. Gandha, Gandhekli describes some recipes for making scents, mouth perfumes, bath powders, incense, and talcum powder. Paper was known to India in the 17th century as account of the Chinese traveler. First testing describes excavations at Textila indicate that ink was used in India from the 4th century. Colors of ink were made from chalk, red lead, and minimum. It seems that the process of fermentation was well known to Indians. Our Vedas and Kautilya's Arthashastra mention about many types of liquors. Charaka Samhita also mentions ingredients such as barks of plants, stem, flowers, leaves, weeds, woods, cereals, fruits, and sugarcane for making asavas. The concept that matter is ultimately made of individual building blocks appeared in India a few centuries BCE as a part of philosophical speculations. Acharya Kanda Acharya Kanda, born in 600 BC, originally known by the name Kashyap, was the first proponent of the atomic theory. He formulated the theory of very small individual particles which he named Paramanu, a comparable of atom. He authorized the next Vaisehika, aggregated form of sutras. Vaisika Sutras, according to him, all substances are aggregated form of smaller units called atoms, Parmanu, which are eternal, indestructible, spherical, suprasensible, and in motion. In the original state, he explained that this individual entity cannot be sensed through any human organ. Kanda added that there are varieties of atoms that are as different as the different classes of substances. He said this Parmanu could form pairs of triplets among other combinations, and unseen forces cause interaction between them. He conceptualized this theory around 2500 years before John Dalton, 1766 to 1844. Charaka Samhita is the oldest and Ayurvedic epic of India. It describes the treatment of disease, the concept of reduction of concept of the reduction of particle size of metals is clearly discussed in Charaka Samhita. The extreme reduction of particle size is termed as nanotechnology. Charaka Samhita describes the use of bhasma of metals in the treatment of alignment. Nowadays, it was It has been proved that plasmas have nanoparticles of metals. After the decline of alchemy electrochemistry reached a steady state, but it would too declined due to the introduction of practice of Western medicinal system in the 20th century. During this period of stagnation, pharmaceuticals industry based on Ayurveda continued to exist, but it too declined gradually. It took about 100 to 150 years of for Indians to learn and adapt new techniques. During this time, foreign products poured him as a result. Indigenous traditional techniques gradually declined. Modern science appeared in India seen in the latter part of the 19th century. By the mid 19th century, European scientists started coming to India and modern chemistry started growing. From the above discussion, now you have learned that chemistry deals with the composition, structure, properties, and interaction of matter, and is of much use of human beings in daily life. These aspects can be best described and understood in terms of basic constituents of matter, that the atoms and molecules. That is why chemistry is also called as science of atoms and molecules. Can we see weigh and oversee on these entities, atoms and molecules? It is possible to count the number of atoms and molecules in a given mass of matter and have a quantitative relationship between the mass and number of these particles. We will get the answer of some of these questions in this unit. We will further describe how physical properties of matter can be quantitative described using numerical value with suitable units. Importance of chemistry. Chemistry plays a central role in science and is often intertwined with other branches of science. Principles of chemistry are applicable in diverse areas such as weather patterns, functioning of brain and operation of computer, production in chemical industries, manufacturing fertilizers, alkalis, acids, salts, dyes, polymers, drugs, soaps, detergents, metal alloys, etc., including new material. Chemistry contributes in a big way to the national economy. It also plays an important role in the meeting human needs for food, healthcare products, and other material aimed at improving the quality of life. This is exemplified by the large scale production of a variety of fertilizers, improved variety of pesticides and insecticides. Chemistry provides methods for the isolation of life-saving drugs from natural sources and makes possible synthesis of such drugs. Some of these drugs are cisplatin and Taxol, which are effective in cancer therapy. The drug agent azidothymidine is used for helping AIDS patients. Chemistry contributes to a large extent in the development of growth of a nation. With a better understanding of chemical principles, it has now become possible to be design and synthesize new material having specific magnetic, electric, and optical properties. This has led to the production of superconducting ceramics, conducting polymers, optical fibers, etc. Chemistry has helped in establishing industries which manufacture utility goods like acids, alkalis, dyes, polymer, metals, etc. These industries contribute in a big way to the economy of a nation and generates employment. In recent years, chemistry has helped in dealing with some of the passing aspects of environmental degradation with a fair degree of success. Suffer alternatives to environmentally hazardous refrigerants CFCs, chlorofluorocarbons, are responsible for ozone depletion in the stratosphere, have been successfully synthesized. However, many big environmental problems continue to be matters of grave concern to the chemistry. One such problem is the management of the greenhouse gases like methane, carbon dioxide, etc. Understanding of biochemical processes, use of enzymes for large scale production of chemicals and synthesis of new exotic material are some of the intellectual challenges for the future generation of chemists. A developing country like India needs talented and creative chemists for accepting such challenges. To be a good chemist and to accept such challenges, one needs to understand the basic concepts of chemistry, which begin with the concept of matter. Let us start with the nature of matter. 1.2 Nature of matter. You are already familiar with the term matter from your earlier classes. Anything which has mass and occupies space is called matter. Everything around us, for example, book, pen, pencil, water, air, all living beings, etc., are composed of matter. You know that they have mass and they occupy space. Let us recall the characteristic of the states of matter which you learned in your previous classes. 1.2 Nature of matter. You are already familiar with the term matter from your earlier classes. Anything which has mass and occupies space is called matter. Everything around us, for example, book, pen, pencil, water, we are all living beings, etc., are composed of matter. You know that they have mass and they occupy space. Let us recall the characteristics of the states of matter which you learned in your previous classes. Well, states of matter. You are aware that matter can exist in the three physical states while solid, liquid, and gas. The constituent particles of matter in these three states can be represented as shown in figure 1.1. Particles are held very close to each other in solids in an orderly fashion, and there is not much freedom of movement. In liquids, the particles are close to each other, but they are move around. However, in gases, the particles are far apart as compared to those present in solid and liquid states, and their movement is easy and fast because of such arrangement of particles. Different states of matter exhibit the following characteristics. Solids have definite volume and definite shape. Liquids have definite volume but do not have definite shape. They take the shape of the container in which they are they are placed. Third, gases have a neither definite volume nor definite shape. They completely occupy the space in the container in which they are placed. These three states of matter are interconvertible by changing the conditions of temperature and pressure, solid, liquid, and gases. On heating, the solid usually changes the liquid, and the liquid on further heating changes to gas or vapor. In the reverse process, a gas on cooling liquefies to the liquid, and the liquid on further cooling freezes to the solid. Classification of matter. In class 9, chapter 2, you have learned that the microscopic on the or bulk level, the matter can be classified as mixture or pure substance. This can be further subdivided as shown in figure 1.2. The when all constituent particles of substance are same in chemical nature, it is said to be a pure substance. A mixture contains many types of particles. A mixture contains particles of two or more pure substances, which may be present in to any ratio. Hence, their composition is variable. Pure substances forming mixture are called its components. Many of the substances present around you are mixtures. For example, sugar solution and in sugar solution in water, air, tea, etc. are all mixtures. In a mixture, many be homogeneous and heterogeneous. In a homogeneous mixture, the components completely mix with each other. This means particles of components of the mixture are uniformly distributed throughout the bulk of the mixture, and its composition is uniform throughout. Sugar solution and air are the examples of homogeneous mixtures. In contrast to this, in a heterogeneous mixture, now the composition is the not uniform throughout throughout, and sometimes different components are visible. For example, mixtures of salt and sugar, grains of pulses along with some dirt, often stone pieces, are heterogeneous mixtures. You can think of many more examples of mixtures which you come across in the daily life. It is worthwhile to mention here that the components of mixture can be separated by using physical methods such as simple hand picking, filtration, crystallization, distillation, etc. Pure substances have characteristics different from mixtures. Constituent particles of pure substances have fixed composition. Copper, silver, gold, water, and glucose are some examples of pure substances. Glucose contains carbon, hydrogen, and oxygen in a fixed ratio, and its particles are of the same composition. Hence, like all other pure substances, glucose has a fixed composition. Also, its constituents carbon, hydrogen, and oxygen cannot be separated by simple physical methods. Pure substances can further be classified into elements and compounds. The particles of an element consist of only one type of atoms. These particles may exist as atoms or molecules. You may be familiar with the atoms and molecules from the previous classes. However, you will be studying about them in detail in Unit 2. Sodium, copper, silver, hydrogen, oxygen, etc. are some examples of elements. There all atoms are of the one type. However, the atoms of different elements are different in nature. Some elements, such as sodium or copper, contain atoms as their constituent particles, whereas in some others, the constituent particles are molecules, which are formed by two or more atoms. For example, hydrogen, nitrogen, and oxygen gases consist of molecules in which molecules. This is illustrated in Figure 1.3. 1.3 are representation of atoms, atoms and molecules. When two or more atoms of different elements combine together in a definite ratio, the molecule of compound is obtained. Moreover, the constituents of a compound cannot be separated into simpler substances by physical methods. They can be separated by chemical methods. Examples of some compounds are water, ammonia, carbon dioxide, sugar, etc. The molecules of water and carbon dioxide are represented in Figure 1.4. Note that a water molecule comprises two hydrogen atoms and one oxygen atom. Similarly, a molecule of carbon dioxide contains two oxygen atoms combined with one carbon atom. Thus, the atoms of different elements are present in a compound in a fixed and definite ratio, and this ratio is characteristic of a particular compound. Also, the properties of a compound are different from those of its constituent elements. For example, hydrogen and oxygen gases, whereas the compound formed by their combination, that is water, is a liquid. It is interesting to note that hydrogen burns with the pop sound, and oxygen is a supporter of combustion, but water is used as a fire extinguisher. Properties of matter and their measurement. Physical and chemical properties. Every substances has unique or characteristic properties. These properties can be classified into two categories: physical properties such as color, odor, melting point, boiling point, density, etc., and chemical properties like composition, combustibility, reactivity with the acids and bases, etc. Physical properties can be measured or observed without changing the identity of or the composition of the substance. The measurement or observation of chemical properties requires a chemical change to occur. The measurement of physical properties does not require occurrence of a chemical change. The examples of chemical properties are characteristic reactions of different substances. Now, this includes acidity of basicity, combustibility, etc. Chemists describe, interpret, and predict the behavior of substances on the basis of knowledge of their physical and chemical properties. Now, which are physical and chemical properties which are determined by careful measurement and experimentation. In the following section, we will learn about the measurement of physical properties. Measurement of physical properties. Quantitative measurement of properties is required for scientific investigation. Many properties of matter, such as length, area, volume, etc., are quantitative in nature. Any quantitative observation or measurement is represented by a number followed by units in which it is measured. For example, length of a room can be represented as 6 meter. Here 6 is the number and meter denotes m denotes meter. The unit is in which the length is measured. Earlier, two different systems of measurement, that is the English system and the metric system, were being used in different parts of the world. The metric system, which organized or originated in France in late 18th century, was more convenient as it was based on the decimal system. Late in need of a common standard statement system was felt by the scientific community. Such a system was established in 1960 and is discussed in detail below. The International System of Units (SI), the International System of Units in French, Les Système International D units, the abbreviated as SI, that was established by the 11th General Conference on Weights and Measures CGPM from Conference General for Days Points at measures. The CGPM is an intergovernmental the treaty organization created by a diplomatic treaty known as Meter Convention, which was signed in Paris in 1875. The SI system has seven base units and they are listed in table 1.1. These units pertain to the seven fundamental scientific quantities. The other physical quantities such as speed, volume, density, etc., can be derived from these quantities. Length, mass, time, electric current. Table 1.1, base physical quantities and their units. Base physical quantity: the length, mass, time, electric current, thermodynamic temperature, amount of substance, and luminous intensity. The name of SI unit: meter, kilometer, kilogram, second, ampere, Kelvin, mole, and Canada. The definitions of the SI base units are given in table 1.2. The SI unit allows the use of prefixes to indicate the multiples of sub-multiple of a unit. Now, these prefixes are listed in table 1.3. Let us now quickly go through some of the quantities which you will be often using in the book. Table 1.2, definitions of SI base units. Unit of length, unit of mass, unit of time, unit of electric current, unit of thermodynamic temperature, unit of amount of substance, and unit of luminous intensity. Table 1.3, prefixes used in the SI system: octo, apecto, atto, femto, pico, nano, micro, milli, centi, deci, deca, hecto, kilo, mega, giga, tetra, peta, and exa, zeta, iota. 1.3.4, Mass and weight. Mass of a substance is the amount of matter present in it, while weight is the force exerted by gravity on an object. The mass of a substance is constant, whereas its weight uh, may vary from one place to another due to change in gravity. You should be careful in using these terms. The mass of a substance can be determined accurately in the laboratory by using an analytical balance. The SI unit of mass as given in table 1.1 in kilogram. However, its fractions named as gram, 1 kilogram is equal to 1000 gram, is used in laboratories due to the smaller amounts of chemicals used in chemical reactions. Volume is the amount of space occupied by the substance. It has the units of length square. Now, so in SI length cube, so in the SI unit, volume has units of meter cube. But again, in chemistry laboratories, smaller volumes are used. Hence, volume is often denoted in centimeter cube or cube units. A common unit liter, capital L, which is not an SI unit, is used for measurement of volume of liquid. Capital L is equal to 1000 milliliter, 1000 centimeter cube is equal to 1 dm cube. 1.6 helps to visualize the relations. In the laboratory, the volume of liquids or solutions can be measured by the graduated cylinder, burette, pipette, etc. The volumetric flask is used for to prepare a known volume of a solution. This measuring device are shown in figure 1.7. Some volume measuring devices. The density. The two properties, mass and volume, discussed above are related as follows. Density is equal to mass upon volume. Density of a substance is its amount of mass per unit volume. So SI units of density can be obtained as follows. SI unit of density is equal to SI unit of mass upon SI unit of volume. Kilogram upon meter cube is equal to kilogram per meter cube. And this unit is quite large, and the chemist often expresses density in gram per centimeter cube, where mass is expressed in gram and volume is expressed in centimeter cube. Density of a substance tells us about how closely its particles are packed. If density is more, it means particles are more closely packed. Temperature. There are three common scales to measure temperature: degree Celsius, degree Fahrenheit, and degree and Kelvin. And here K is the SI unit. The thermometers based on these scales are shown in figure 1.8. Generally, the thermometer with Celsius scale are calibrated from 0 degree to 100 degree, where these two temperatures are the freezing point and the boiling point of water, respectively. The Fahrenheit now scale is represented between 32 degree to 212 degree. The temperatures on two scales are related to each other by the following relationship: degree Fahrenheit is equal to 9 by 5 degree Celsius plus 32. The Kelvin scale is related to Celsius scale as follows: K is equal to degree Celsius plus 273.15. It is interesting to note that temperature below 0 degree Celsius, that is negative values, are possible in Celsius scale, but in Kelvin scale negative temperature is not possible. For university uncertainty uncertainty in measurement, many are time in the study of chemistry, one has to deal with experimental data as well as theoretical calculations. There are meaningful ways to handle the numbers conveniently and present the data realistically with certainty to the extent possible. Those These ideas are discussed below in detail. Scientific notation, as chemistry in the is the study of atoms and molecules which have extremely low masses and are present in extremely large numbers. A chemist has to deal with the numbers of as large as 602200000000003 4 times for the molecules of 2 gram of hydrogen gas or as small as molecules of 2 gram of hydrogen gas small as 0.00000000001.66 gram mass of hydrogen atom. Similarly, other constants such as Planck's constant, speed of light, charges on particles, etc., involve numbers of above magnitude. It may look funny for a moment to write or count numbers involving so many zeros, but it offers a real challenge to do simple mathematical operations of addition, subtraction, multiplication, or division. Now, with such numbers, you can write any two numbers of the above type and try any one of the operations you like to accept as the challenge, and then you will really appreciate the difficulty in handling such numbers. This problem is solved by using scientific notation for such numbers, that is exponential notation, in which then any number can be represented in the form n. Capital N is equal to 10 to the power small n, where small n is the exponent with the exponent having positive and negative values, and capital N is a number called digit term which varies on between 1000 to 1.0002 to infinite and 9.000 to infinite. Thus, we can write 232.508 as 2.32508 into 10 to the power 2 in scientific notation. Note that in the left by the two places, and same is the exponent 2 onto the in the scientific notation. Similarly, 0.00016 can be written as 1.6 into 10 to the power minus 4. Here the decimal has to be moved 4 places to the right, and minus 4 is the exponent in the scientific notation. While performing mathematical appearance operations on numbers expressed in scientific notations, the following points are how to be kept in mind: multiplication and division, addition and subtraction. For this two operations, first the numbers are written in such a way that they have the same exponent. After that, the coefficients digit terms are added or subtracted as the case or maybe. Thus, for adding 6.65 into 10 to the power 4 and 8.95 into 10 to the power 3, exponent is made same for both the numbers. Thus, we get 6.65 into 10 to the power 4 plus 0.895 into 10 to the power 4, and then these numbers can be added as follows: 6.65 into plus 0.895 into 10 to the power 4 is equal to 7.454 into 10 to the power 4. Significant figures: every experimental measurement has some amount of uncertainty associated with it because of limitation of measurement instrument and the skill of a person making the measurement. For example, mass of an object is obtained using a platform at the balance, and it comes out to be 9.4 gram. On measuring the mass of this object on an analytical balance, the mass obtained is 9.4 to 213 gram. The mass obtained by an analytical balance is slightly higher than the mass obtained by using a platform balance. therefore digit 4 placed after decimal in the measurement by platform balancing is uncertain. Thus, uncertainty in the experimental for the calculated values is indicated by mentioning the number of significant figures. Significant figures are meaningful digits which are known with certainty plus uncertainty certainty plus one which is estimated or uncertain. The uncertainty is indicated by writing the certain digits and the last uncertain digits. Thus, if we write a result as 11.2 milliliter, we say the 11 is certain and 2 is uncertain, and the uncertainty would be plus minus 1 in the last digit unless otherwise stated. And uncertainty of plus minus 1 in the last digit is always understood. There are certain rules for determining the number of significant figures as the stated below. All non-zero digits are significant. For example, in 285 centimeter, there are three significant figures, and in 0.25 milliliter, there are two significant figures. Zeros preceding to first non-zero digit are not significant. Such zero digit indicates the position of decimal point. Thus, point zero three has one significant figure, and point zero zero five two has two significant figures. Zeros between two non-zero digits has significant. Thus, 2.05 has four significant figures. Zeros at the end or the right of a number are significant, and provided they are on the right side of the decimal point. For example, point 200 gram has three significant number figures, but if otherwise the terminal zeros are not significant if there is no decimal point. For example, 100 has only one significant figure, but 100 has three significant figure. 100 100 has three significant figures, and 100.0 has four significant figures. Such numbers are better and are represented in scientific notation. We can express the number 100 as 1.1 into 10 to the power 2 for one significant figure. 1 point for one significant figure, 1 point into 10 to the power 2 for two significant figures, and 1.00 into 10 to the power 2 for three significant figures. Counting the numbers of objects, for example, two balls or 20 eggs have infinite significant figures, as these are the exact numbers and can be represented by weighting infinite number of zeros after placing a decimal, that is 2 is equal to now 2.000000 of 20 into 20.000000, the number written in specific notation. All digits are significant. Example 4.1, 4.01 into 10 to the power 2 has the three significant figures, and 8.2656 into 10 to the power minus 3 has four significant figures. However, one would always like the results or to be precise and accurate. Precision and accuracy are often referred while we talk about the measurement. Precision refers to the closeness of various measurements of the same quantity. However, accuracy is the agreement of a particular value of the true value of the result. For example, if the true value of for the result 2 gram 2.00 gram, and the student it takes two measurements of report and reports the results is as 1.95 gram and 1.93 gram. These values are precise as they are close to each other but are not accurate. Another student B repeated the experiment and obtained 1.94 gram and 2.05 gram as the results of two for two measurements. These observations are neither precise nor accurate. When the third student C repeats these measurements and reports 2.01 gram and 1.99 gram as the result. These values are both precise and accurate. This can be more clearly understand from the given data in table. Addition and subtraction of significant figures. The result cannot have more digits to the right of the decimal point than either of the original numbers. Here 18.0 has only one digit after the decimal point, and the result should be reported only up to one digit after the decimal point, which is 31.1. Multiplication and division of significant figures. Dimensional analysis. Solutions. Laws of chemical combinations. Law of conservation of mass. Law of chemical combination. The combination of elements to form compounds is governed by the following five basic laws. Law of conservation of mass. This law was put forth by Antoine Lavoisier in 1789, and he performed careful experimental studies for combustion reactions and reached to the conclusion that in all the physical and chemical changes there is there is no net change in mass put during the process. Hence, they reached to the conclusion that matter can neither be created nor destroyed. This is called the law of conservation of mass. This law formed the basis for several later developments in chemistry. In fact, this was the result of exact measurement of masses of reactants and products and the carefully planned experiments performed by Lavoisier. Law of definite properties. This law was given by French chemist Joseph Proust. He stated that a given compound always contains exactly the same proportion of elements by weight. Proust world was with two samples of cupric carbonate, one of which was of natural origin and the other was synthetic. He found that the composition of element present in it was same for both the samples as shown in below. Thus, the concluded that irrespective of the source, a given compound always contains same elements combined together in the same proportion by mass. The validity of this law has been confirmed by various experiments, so it is sometimes also referred to as law of definite composition. Law of multiple proportions. This law was proposed by Dalton in 1803. According to this law, if two elements can combine to form more than one compound, one masses of an element that combine with the fixed mass of other element are in the ratio of small whole numbers. For example, hydrogen combines with oxygen to form two compounds, namely water and hydrogen peroxide. Gay-Lussac's law of gaseous volumes. This law was given by Gay-Lussac in 1808. 1808. He observed that when gases combine or are produced in a chemical reaction, they do so in a simple ratio by volume, provided all gases are at the same temperature and pressure. Thus, 800 milliliter of hydrogen combined with 50 milliliter of oxygen to give 100 milliliter of water vapor. Thus, the volumes of hydrogen and oxygen which combine and bear a simple ratio of 2:1. Gay-Lussac's discovery of integer ratio of volume relationship is actually the law of definite proportions of by volume. The law of definite proportions stated earlier was with respect of mass. The Gay-Lussac's law was explained properly by the work of Avogadro in 1811. Avogadro's law, 1811, Avogadro proposed that equal volumes of all gases at the same temperature and pressure should contain equal number of molecules. Avogadro made a distinction between atoms and molecules, which is quite understandable. Uh, in present times, if we consider again the reaction of hydrogen and oxygen to produce water, we see that two volumes of hydrogen combine with one volume of oxygen to combine two volumes of water without leaving any unreached oxygen. Note that in the figure 1.9, page 16, each box contains the equal number of molecules. In fact, Avogadro could explain the above result by considering the molecules of bar to be polyatomic in hydrogen and oxygen were considered as diatomic as recognized now. Then the above results are easily understandable. However, Dalton and others delivered at that time that atoms of the same kind cannot combine and molecules of oxygen or hydrogen containing two atoms did not exist. Avogadro's proposal was published in the French journal de Physique. In spite of being correct, it did not gain much support. After about 50 years in 1960, the first international conference on chemistry was held in Karlsruhe, Germany, to resolve various ideas. At the meetings, Stanislaw Canizaro presented a sketch of the course of chemical philosophy, which emphasized on the importance of Avogadro's work. Dalton's atomic theory also the origin of idea that matter is composed of small individual particles called atomio, meaning individual, dates back to the time of Democritus, the Greek philosopher 460 to 370 BC. It again started engineering as a result of several experimental studies which led to the laws mentioned above. In 1808, Dalton published a new system of chemical philosophy in which he proposed the following: matter consists of individual atoms. All atoms of a given element have identical properties, including identical mass. Atoms of different elements differ in mass. Compounds are formed now when atoms of different elements combine in a fixed ratio. Chemical reactions involve organization of atoms. This are neither created nor destroyed in a chemical reaction. Dalton's theory could explain the laws of chemical combination, however, it could be not explain the laws of gases gaseous volumes. It could not provide the reasons for combining of atoms, which was answered later by other scientists. Atomic and molecular masses. After having some idea about the terms of atoms and molecules, it is appropriate here to understand what do we mean by atomic and molecular mass. Atomic mass, average atomic mass, molecular mass, formula mass, mole concept and molar masses, percentage composition, empirical formula for molecular formula, stoichiometry and stoichiometric calculations, limiting reagent, reactions in solutions, balancing a chemical equation, mass percent. Mass percent is equal to mass of solute upon mass of solution into 100. Mass fraction. Mole fraction of A is equal to number of moles of A upon number of moles of solutions. Molarity. Number of moles of solute upon number of moles of liters. Molality, number of moles of solute upon number of mass of solvent in kilogram. Then summary. Some basic concepts of chemistry. Summary. Chemistry, as we understand how it today, is not a very old discipline. People in ancient India city already had the knowledge of many scientific phenomena so much before the advent of modern science. They applied the knowledge in various walks of life. The study of chemistry. The study of chemistry is very important as its domain encompasses every sphere of life. Chemists study the properties and structure of substances and the changes undergone by them. All substances contain matter which can exist in three states: solid, liquid, or gases. The constituent particles are held in different ways in the states of matter, and they exhibit their characteristic properties. Matter can also be classified into elements, compounds, and mixtures. An element contains particles of only one type, which may be atoms or molecules. The compound are formed where atoms of the two or more elements combine in a fixed ratio or to each other. Mixtures occur widely, and many or two of the substances present around us are mixtures. When the properties of substance are studied, measurement is inherent. The quantification of properties requires a system of measurement and units in which the quantities are to be expressed. Many systems of measurement exist, of which the English and metric systems are widely used. The scientific community, however, has agreed to have a uniform and common system throughout the world, which is abbreviated as SI units, International System of Units. Now, since measurements involve according to data which are always associated with a certain amount of uncertainty, and the proper handling of data obtained by measuring of quantities is very important. The measurements of quantities of in chemistry are spread over a wide range of 10 is to power 31 and 10 is to 2 power 23. Hence, the convenient system of expressing the numbers in scientific notation is used. The uncertainty is taken care by specifying the number of significant figures in which the observations are reported. The dimensional analysis helps to express the measurement on measured quantities in different systems of units. Hence, it is possible to interconvert the result from one system of units to another. The combination of different atoms is governed by basic laws of chemical combination, these being the law of conservation of mass, law of definite proportion, law of multiple proportions, Gay-Lussac's law of gaseous volumes, and Avogadro law. All these laws led to the Dalton's atomic theory, which states that atoms are building blocks of matter. The atomic mass of an element is expressed relative to its carbon 12 isotope of carbon, which has the exact value of 12 U. Usually, the atomic mass used for an element of is the average atomic mass obtained by taking into account the natural abundance of different average atomic mass obtained by taking into account the natural abundance of different isotopes of that element. The molecular mass of molecule is obtained by taking sum of the atomic masses of different atoms present in a molecule. The molecular formula can be calculated by determining the mass percent of different elements present in a compound and its molecular mass, the number of atoms, molecules, and any other particles present in a given systems are expressed in the term of Avogadro constant 6.022 into 10 raised to power 23. This is known as 1 mole of as respect to particles of entities. Chemical reactions represent the chemical changes undergone by different elements and compounds. A balanced chemical equation provides a lot of information. The coefficients indicate the molar ratios and the respective number of particles taking part in a particular reaction. The quantitative study of the reactants required or the products formed is called stoichiometry. Using stoichiometry calculations, the amount of one or more reactants are required to produce the particular amount of product can be determined, and vice versa. The amount of substance present in a given volume of a solution is expressed in number of ways. The example mass percent, mole mass fraction, and molarity and molality. सम बेसिक कॉन्सेप्ट्स ऑफ केमिस्ट्री यूनिट 1 है जिसमें हमने पहले से देखा डेवलपमेंट ऑफ केमिस्ट्री, देन उसके बाद इम्पोर्टेंस ऑफ केमिस्ट्री, नेचर ऑफ मैटर, स्टेट्स ऑफ मैटर, क्लासिफिकेशन ऑफ मैटर, then for properties of matter and their measurement, physical and chemical properties, measurement of physical properties, the international system of units, SI units, prefixes used in the SI units, mass and weight, volume, then density, then temperature, then uncertainty in measurement, then scientific notation, then multiplication and division, then addition and subtraction, then significant figures के rules, then multiplication and division of significant figures, then laws of chemical combination, then law of conservation of mass, then law of definite proportions, then law of multiple proportions, then Gay-Lussac's law of gaseous volumes, then Avogadro law, then Dalton's atomic theory, then atomic and molecular masses, atomic mass, average atomic mass, molecular mass, formula mass, mole concept and molar masses, percentage composition, empirical formula for molecular formula, conversion of mass percent to grams, convert into number of moles of each element, divide each of the mole volume values obtained above by the smallest number of amongst them, write down the empirical formula by mentioning the numbers after writing the symbols of respective elements, writing molecular mass formula, stoichiometry and stoichiometric calculations, limiting reagent, reactions in solutions, mass percent, mole fraction, molarity, then summary. सम बेसिक कॉन्सेप्ट्स ऑफ केमिस्ट्री फर्स्ट यूनिट है जिसमें हमने ये सब देखा. प्लीज़ लाइक शेयर एंड सब्सक्राइब. थैंक यू सो मच फॉर वॉचिंग.